Hi, this is Mladen Jovanovic from complementarytraining.net, and in this video I would like to talk about one potential method that we can use to compare individuals between and within themselves across time using load velocity profile. So in this simple example, let's assume the athletes are lifting hex bar deadlift, and we have three athletes. This could be three different athletes, or it could be, as in this case, one athlete pre and post, and we just want to see different metrics of kind of aggregating the information about the load velocity table, load velocity profile, see how they relate to each other, and so forth. So just to begin with, we have external load. Total load I'm going to cover later. In this case, it's equal to external load. We have relative load divided by body weight, and we have velocity. So let's see the orange guy. What we can calculate from this load velocity profile is we can calculate L0, which is load at zero velocity. This is bigger than 1 RM because with 1 RM we still need to we are still lifting with certain velocity, and that's around, again, depends on the device and depends on the movement, 0.15 meters per second for a bench presser and around 0.3 for a squat. So again, this extends the line to an intercept between the horizontal line. And as you can see in the chart, I didn't plot the external absolute loads. I plot the relative load, which is weight divided by body weight. Then we also have V0, which is velocity when the load is zero. Again, this is actually the intercept, and this is a vertical intercept, and it extends over this range. And in this case, because we are using absolute loads, basically means doing exercise with the body weight only. Area under curve is one of the metrics we can use to kind of integrate all the information across data points. So this is basically just a surface under the curve, and as we can see, we have 2 points, so V0 and L0, and then what we form is a triangle, so you can calculate the surface of that triangle. So this is approximation of area under curve, of course, because the curve might be slightly non-linear, so we can use more advanced metrics, advanced regression, nonlinear regression to estimate it. But in this case, since we're using linear regression, it makes sense to extend it and use a surface of the triangle. As we can see, athlete number 1, the orange guy, and the blue guy, let's assume that's the same guy. We see a shift in load velocity profile, and we can see that L0 increased, which is assumed. We see that V0 increased as well, and area under curve increased. What's tricky now is it's easy to compare one athlete across time, but what if you're comparing two individuals and they might differ in body weight? So in this case, we use this is a gray athlete that we can see has a faster velocity compared to those two athletes, but has lower 1 RM. If we use absolute loads, we see that area under curve is much smaller than other guys, although V0 is bigger. So these guys can lift lower loads faster. But if we want to compare across the players, we need to take body weight into account. So in this case, I use relative load, which is the total load. In this case, it's similar. It's same as external load, divided by body weight, and that's this chart we created over here. In this case, we calculate L0, which is same thing as L0 divided by body weight, and V0 is again same. What we get is this more relative area under curve, and we can use that to compare the individuals. As you can see, now the gray guy, even when his area under curve is smaller, using absolute loads, is bigger when we use relative loads because he's lighter. And this means compared to his body weight, these guys have a, I would say, bigger area under curve, and that can mean, and that takes the whole continuum into account. So taking his load velocity profile, he's able to kind of hard to try to put that in words. So his profile is bigger. So area under curve is bigger, but even if he's more suited to lifting lower loads faster. Again, that's why it's very important to plot all the data. But anyway, we can use this to quickly aggregate. The blue guy, even when we make things more relative, is again the strongest because he has the biggest area under curve. Let's assume this guy is also gain weight. It's still again better than everyone else. So let's increase this a little more. Yeah, so now we can see the effect of gaining weight as well. What's important, and this is also built inside these metrics, is the we need to adjust for heavier guys because we have a bias toward the lighter guys. So the heavier guys are lifting, for example, in squat, they might be lifting 80% of their body weight when there is zero external resistance. So we can use that also to kind of correct for the bias. So let's say in this example, we lift the upper body and thighs. So that's around 80% of the body weight. We can use precise tables, but let's say we use 80. Now the total load changed. You can see here. But what we can do now is to, now we are analyzing the curve using using this corrected relative load. Yeah, so the graph took some time to adjust. Yeah, so now we can we have L0, which is again external load. Total load divided by body weight when velocity is 0, and we have V0, which is velocity when total load is 0. Again, this is basically in unloaded movement, so it's not really much related to anything physical, realistic. So this is, in this case, because we use 80%, that means we need to strip off 80% of body weight, and then we're gonna get this velocity approximately. Not so sure, so I can double check the metric. Anyway, now we have different areas on the curve, and we can see our gray guy, the lighter individual, is pretty much similar with area under curve when we compare to the heavier guy. So again, different ways to analyze and different ways to aggregate the data, and in my opinion, we should use either, because in this scenario we can compare individuals across time, and we can compare between individuals of different body weight and different 1RMs. So using this three parameters, area under curve, and L0 and V0 can give us basically a full profile of load velocity for each individual athlete. Again, some of the things are much more easier to understand because the intercept is realistic. In this case, when we use absolute and relative loads, but when we use corrected total system load, then it's a little bit more tricky to give up a particular meaning to these intercepts and area under curve. Again, but I guess this is a way to go to compare the athletes. So this could be useful in creating leaderboards across loads. So when you want to create a leaderboard and you want to compare different athletes of different characteristics and different body weights, we can use area under curve to take into account, again, different body weight, different 1RMs, and different, the whole continuum of load velocity profile. Thanks for watching, and hope this gave you a couple of ideas.